Hello everyone, this is Kate from Lamina, and first of all, thank you for your valuable time for this webinar. I'm going to talk about the way of easy scale up and also how to improve the productivity with our Taylor Reactor LCTR series. LCTR stands for Lamina's Continuous Taylor Reactor. My presentation will take about 20 minutes and is divided into 6 sections based on 5W and 1H. First, I'm going to talk about the challenges that people face during the development and production and when LCTR is needed. Then I will explain why LCTR is possible to solve the problem with the proof. After that, I will show you how LCTR works, where LCTR is used for, and what LCTR is most suitable for you. Finally, I'll introduce ourselves. First, when is LCTR needed? There are so many challenges for the time from development to the mass production. At the development stage, researchers search for the experiments that have previously done and new conditions. Through a lot of trials and errors, they finally find the optimized conditions for the new material. After the long development, the new stage comes up, which is scale up to production. However, at this stage, everyone faced the common challenge, which is the good results they got at the laboratory didn't come up at the production site. So many people spend a lot of time to try with various parameters to search the optimized conditions for the mass production. Also, some just changed reactors. I'm sure the pictures are very familiar with you. These are tank-type batch reactor and plug flow reactor. What do you think the results will be same between lab and factory if you just change the reactor? Actually, there are some pros and cons with the batch and PFR. For batch, it is easy to operate and technically easy to scale up, but it is hard to produce uniform particles and you will have such a long production time. For PFR, high purity materials can be produced and the properties are good due to the high reproducibility. However, there are some mentioned issues like powders are stuck in the pipe and low productivity due to the limitation of the scale up. However, our LCTR reactor combines the benefits of batch and PFR. It is very easy to operate and it is also easy to scale up mechanically and chemically. Also, the production time can be shortened and the productivity will be increased as it can produce materials continuously. What makes this possible is the flow. For flow, there are lamina and turbulence flow. As you can see the picture of candle, the lamina is a straight flow without being disturbed. Turbulence is irregular flow like waves and fast-flowing rivers. Lamina flow is not used in the reactor because it has no mixing power. So turbulence is used for batch and PFR. However, because of the use of irregular flows, the particles are randomly mixed, so it is a lack of reproducibility. Therefore, if you scale up with the batch or PFR, you won't get the great result that you got from the lab. However, our Taylor reactor is utilizing the Taylor flow, which is the transit area between lamina and turbulence. As you can see the picture in the middle, Taylor flow is mixing particles homogeneously within the Taylor vertex and brings the high reproducibility. So our Taylor reactor is easy to scale up thanks to the vertex. Now I'm going to talk about why LCTR is possible with the easy scale up and show you the proof. This slide shows CFD data for Taylor flow. Normally, Taylor flow is not quite visible, so CFD is used to see Taylor flow. Taylor vertex consists of a pair of two rings with 1:3 ratio. One Taylor vertex can be considered as one reactor. For example, if there are 14 vertices in 1000 liter LCTR reactor, then you can consider that 14 of 71 liter batch reactors are running at the same time. Unlike the batch with the micro mixing, our LCTR reactor is micro mixing. Once the particles are formed, vertex is not mixed with each vertex, and the particles are moved to the side at the flow rate of the pump set for the reaction time. What do you think, which one is easier for scale up from 1 liter? Like from 1 liter to 1000 liter reactor, or 1 liter reactor to 14 of 71 liter reactors? Of course, the latter one, 14 reactors, would be much easier. Therefore, even though the working volume of batch reactor and our LCTR reactor is same, our LCTR reactor is much easier to scale up, and particles are micro-mixed as our Taylor reactors act as several batch reactors. In fact, when we scale up, we only adjust agitation speed according to the linear velocity. Like shown in the below table, even though the volume increases from 1 liter, 50 liter to 1000 liter, if you control agitation speed, then you can make the same number of the Taylor flow and also get the same results. This shows our 1 liter to 300 liter scale-up project with monoammonium phosphate. As you can see the graph for particle size, recovery rate, purity, and crystallinity, the results of the 1 liter and 300 liter are almost in the same position. This is the second one. Besides of our own experiment, one of the paper mentioned that the results of CFD simulation and real experiments with 10 liter are same. This is the third proof. Argonne National Laboratory in the US has been researching and producing the precursor for the lithium-ion battery, and they were able to produce the material with the same properties from 1 liter, 10 liter, and 40 liters. So now I'm going to show you the principle of the LCTR. But before explaining the principle, let's see the history of the Taylor flow. In 1900, Hoyt found the Taylor flow between lamina and turbulence. In 1950, Taylor made equation for the creation of the Taylor flow. In 2010, with lamina, designed, manufactured, and commercialized the chemical reactor utilizing Taylor flow for the first time in the world. Since the Taylor flow is quite invisible, CFD is the proper tool to see Taylor flow. As you can see the CFD data, the Taylor flow is created within 8 seconds and from the both ends. Taylor flow is generated by two forces of centrifugal and Coriolis and forms the ring pair. One ring moves in clockwise direction and another ring moves in the counterclockwise direction. Here is a video showing the structure of our LCTR reactor. Two cylinders, a rotating inner cylinder and fixed outer cylinder. Reaction zone is the gap between cylinders, and also the temperature control zone is composed of double jackets and temperature is controlled from the outside. Actually, this is the biggest product, which working volume is 1,000 liters. In this video, it shows a horizontal model, but actually we have vertical type too. So it depends on the materials and conditions. We can recommend the right model for you. As you saw the video, solutions are injected from the inlet in the left side. And also in the middle, there are some ports for pH and temperature sensors, and also for the solution too. Also, there are inlets and outlets for the temperature control in the outer jacket. This is what we recorded in our lab. As mentioned before, once the particles are formed, vortexes are not mixed with each other, and the particles are moved to the side. This video shows what I explained. This was the experiment showing different colors based on the pH values. So if pH values are less than 12, it is blue. But if pH is more than 12, then it is pink. As soon as the solutions are injected, you can see that it is not mixed at the end. It moves sideways along the regular Taylor flow. Until now, we go over the principle and how our reactor actually works. From now, I'm going to talk about the application field where LCTR can be used. As mentioned, with the Taylor flow, it is easy scale up from lab to mass production. Also, the high quality materials can be produced continuously. So our LCTR reactor is used in the fields where these advantages are needed. Here's some comparison data between our LCTR reactor and CSTR. Above is the CSTR data, and below is our LCTR data. As you can see the difference, our reactor helps when you want to have high density materials, thin nanocoating, uniform particle size, and spherical particles. And for the time reduction, nano composite, high purity materials, and the precise temperature control during the exothermic reaction. Not only the cases I mentioned, our LCTR reactor can be used in many fields. Now, we are going to see what LCTR is most suitable for you among the different working volume models. Before introducing our product lines, I would like to suggest the process for your better decision. Even with my presentation, you might think about like LCTR reactor is really suitable for me and solve your current challenges. So my suggestion is please simply fill out the questionnaire provided by us. Based on the information from you, we will test under the we will conduct the sample test to determine the applicability of LCTR. Also, upon the request, we can proceed the test under the certain conditions that you want to see with our reactor. After the testing, we will share the results and recommend the most suitable product for you. You don't need to purchase the reactor right away. Please take enough time to review and see our results, and then make a final decision. Also, based on the information and test, we can also recommend not only the standard type of the reactor, but also special types to meet your targets. Our products can be divided into 5 categories. Also, there is a approximate daily production for each model, so you can refer to it. Of course, the production volume varies from the materials to materials, but the calculation was based on the condition that production time is 8 hours per day, solid content is 10%, and reaction time is an hour. LCTR Mini is the smallest one. Working volume is 20 milliliters. Next, we have LCTR Lab 2. Working volumes are 100 milliliters and 200 milliliters. It can produce about 0.16 kilograms per day. Next, LCTR Terra. Its working volume is 1 liter. It depends on the materials, but for the battery, it can be considered as a lab-scaled one, but for another materials, it can be as a pilot-scaled one. With this model, you can produce 0.8 kilograms per day. Next, LCTR Peta. Working volumes are 5 liters, 10 liters, and 50 liters. The daily production volume is about 4 to 40 kilograms. Last, LCTR Axa. This is the mass production reactor, and working volumes are 100 liter, 500 milliliters, and 1000 liters. 80 to 800 kilograms can be produced. We have a variety of product lines, from lab scale to commercial scale. Our reactors can help not only for your research, but also mass production. Finally, I will introduce us. We Lamina are based in South Korea and founded in 2010. We are the world's first company who designed, manufactured, and commercialized the chemical reactor utilizing TeleFlow. We hold 29 patents and apply 1 to 2 patents annually. Also, we have CE certificate covering all our models, and also we have our own R&D center for the sample test. This is the end of my presentation, and thank you for being here today. Please feel free to contact me via email if you have any questions or if you'd like to try with the sample test. We would be more than happy to help you improve your current research and production. Thank you very much.